to be able to run my own slides today. My internet access came back yesterday evening. So today we are going to talk about 3D seismic interpretation. Tuesday past, 2 days ago, we talked about seismic data sets, seismic volume, seismic cubes. And so today we'll talk about how we do some interpretation using the 3D data set. The image up here is a workflow that I'm going to go through as the lecture proceeds. We have a recon phase. We worry about mapping the larger faults, larger offset. Then we worry about mapping some of the key horizons. And then we go back and I'll show you some tools that we can use to look for smaller offset faults. And if we have the major faults and the major horizons, that gives us a faulted framework that sets us up for the next step in our analysis. This slide just recaps the terms of use. It's also on the website where the lectures and exercise materials are located. In essence, it's saying that the materials are designed for the use of students and those that teach students. It is not to be used in any other fashion, especially by people who are already employed or people who are training people that already have a career started. So I'll talk about the workflow. As I mentioned, the first step was to do a reconnaissance. I'll illustrate that. We want to go after the major offset faults. Then we map some of the key horizons. And then we go back and look for some smaller offset faults. So this is the workflow diagram. And so our first step is to do a quick reconnaissance. We want to understand something about the data set and also something about the overall geology. So this is a 3D survey that is from the Gippsland Basin, offshore Australia. It's from the area that a lot of the exercises that accompany the different lectures comes from. So north is slightly skewed, but I'll talk about the east-west lines and north-south lines. For this data set, the inlines, and that means the direction in which the boat sailed north-south, south-north, north-south, those run north-south, and the smaller inline numbers are on the west and they increase. So there's 1500, 2000, 2500. So the numbers increase as we move to the east. The cross lines are perpendicular to the direction the boat sailed. So in this case, I'm going to talk about east-west. The lower numbers, 1000, is on the south. And as I go north, it goes up to 9000. So just understanding the inline direction and in which direction do the numbers increase, also understanding the crossline direction and which direction the crossline numbers increase. That's usually the first thing I do when I get a brand new 3D survey to work on. We can display the amplitudes in different color bars. One that's popular is to have near zero reflection amplitude being white, and the negative values shades of blue, and positive values shades of red. So depending on the polarity, the blues would be perhaps an increase in impedance or a decrease in impedance. The reds would be the opposite. And there's a lot of data points. The aqua is the data density, so the y-axis would be number of samples. There's a lot of zeros, and that's because if I go back a slide, there's no data here, and there's no data here. So all those trace locations would have 0 for the amplitude histogram. And here is one of the lines. I believe this is an inline. And so one of the things we want to do is check the polarity. Are positive reflection coefficients or increases in appearance red, or are they blue? I've talked about that before. For this data set, the water depth is deep enough that we could look at the water bottom reflection, and I have a slide coming up showing that. And the gain is how much we either enhance the amplitude colors or decrease them. So this has a fairly high gain. We're getting really blue blues and red reds. The zone in here where it's less intense in color means it's lower amplitude. And the gain setting is a personal preference. If I had to look at lines like this with this gain setting for 8 hours a day, 5 days a week, 23 days out of the month, I would end up with a headache. So depending on which zone we're looking at, I would think the gain setting here is a little bit too high. This is a time slice, so this is cutting the 3D volume at 200 milliseconds of two-way travel time. Again, the north is skewed a little bit, but you can see if we blow up this area here, you can see some lineations that are running north-south, and those are the acquisition artifacts that I mentioned previously. Some people call them inline stripes. Some people call them, can't think of the other name right offhand. But that is an artifact of not having adequate sampling for the very shallow two-way time depths. As we go deeper, those artifacts will diminish to the point where they're not significant. Here is an inline 4301. So it's a north-south line, and I believe this is to the north, and on the right is to the south. The aqua color line that's kind of jittery through there is what has been interpreted to be the water bottom reflection. When the water gets really shallow, we can't follow it. And so this is telling me for this data set, it looks like blue is an increase in impedance, because one thing that we know is that the water bottom reflection is always an increase in impedance as we go from seawater into even soggy sediments. And so that tells me a little bit about the polarity here. Then we would do a visual inspection, trying to understand some of the major packages. And so it looks like here, the shallowest package, after we get underneath the water bottom, the reflectors are fairly low amplitude, not too deep of a red, not too dark of a black. And the reflectors are not parallel, I might call them subparallel. And then we get into a second package, higher amplitude. These are not as continuous as some of the deeper ones are, so I would say semi-continuous. And in terms of the geometry, I would use a term hummocky. So it's not parallel, it's not subparallel. There's some thickening and thinning going on. Then there seems to be a third package, relatively low amplitude. The reflector geometry here I would call subparallel. And then the fourth main package, very high amplitude, very continuous, broken by some faults. But each of these packages, 1, 2, 3, 4, has somewhat of a different seismic character or seismic texture or seismic facies. So the next step is to try to figure out a bit more detail about where some of the major stratigraphic horizons are, and then what this change in amplitude and continuity all means in terms of the ages and the depositional environments and the lithofacies. And I'll get into that type of analysis later on, not necessarily today, but as the course evolves. It turns out that this low amplitude is the signature for a marine shale, and the higher amplitude continuous reflectors is our primary reservoir in the Gippsland Basin. So if you've been doing some of the exercises, this is the Latrobe Formation, and it has shallow water sands fluvial to near shore to slightly offshore. And then the lake entrance shales sit on top of that. They are part of the sea spray group, and that forms an excellent seal. We can look at a time slice. Now we are at 1200 milliseconds, or 1.2 seconds two-way travel time. And you can see regions like where the number 4 is, where we have the high amplitude continuous reflectors. Number 3, that's our low amplitude semi-continuous subparallel. And so I can look at this time slice and start to see where some of those major packages are. It turns out that this feature here, this oblong cigar-shaped feature, that is the Barracuda anticline. There's another anticline here. There's another anticline over here. The diagram on the lower right says if I have an anticline and if I go from a shallower slice to a deeper slice, then these reflection bands, the blacks and the reds, should spread outward. And conversely, if it was a syncline, as I go deeper, they should converge. And so I can go from 1200 to 1220 to 1240 to 1260, and I don't have an animation for that, but what you'd see is that these reflectors expand out, indicating that this feature, this feature, this feature, and this feature are all anticlines. So we've done our reconnaissance. The next step is to interpret some of the major faults. And I always talk about faults in terms of seismic properties. And so is the offset at a fault about half of a peak or a trough, or less than half, or more than half? Or in the example on the right, this trough is offset to this trough. That's about one time duration for the trough. And so moderate would be a half to 1, and large offset would be more than 1 peak or trough duration in terms of offset. In interpreting the major faults, if we have 2D seismic or if we have 3D, we can look at vertical slices or profiles. And what we would look for as evidence that there's a fault are consistent breaks and reflections along a dipping plane. Sometimes we can see boundaries between zones with different reflection dip. If I have a 3D survey, I can also look at time slices, and on those slices, I can look for boundaries between different reflection packages. And I can also look for zones where there's low continuity from trace to trace, and we can generate a new seismic volume called the coherency, or some people call it semblance, and some people call it various other names. Last Tuesday, I talked about the various names for this cross-correlation volume that we can generate. So here in the image is a piece of the 3D survey. Now I'm looking at a time slice at 1100 milliseconds, and what the white to gray to black is indicating is not reflection amplitude, but a cross-correlation, a trace and its neighbor. So this is a coherency type of data set that I'm looking at. And where I see bands of black, which means low cross-correlation, these are candidates for perhaps 2 different faults. And so what we do is we generate a new data volume, the coherency volume, and then we look at the time slices. We use a grayscale where white and light gray is high cross-correlation, and so not likely that there's a fault offset between a trace and its neighbor. And then the dark grays and blacks are low cross-correlation values, and that means one trace might be on the high side and the next trace is on the low side, or one trace might be on the high side and the next trace is in the fault zone itself. So here is a bigger picture of a coherency type time slice, 1160. And so this is the fault that I had on the previous slide, and this is the second fault. There's another fault here, and one that's important for the Barracuda structure is a fault that cuts through here, and another fault that cuts through there. There's an area here of darker colors, and that is not due to faulting, but there's a very steep dip here, and so a trace and its neighbor may not be highly correlated because of that dip. Some of the advanced coherency algorithms will take reflection dip into account, and so areas of high dip do not show up as coherency anomalies. So let me talk about the process I usually do. I talk about 3 generations of faults. First, I start by manually picking on some vertical sections some of the faults. So these could be inlines and crosslines. It also could be some sort of a traverse or random line. Then those first generation faults I'll post on a time slice, and I can use coherency as an aid, and then I'll start to correlate a second generation of faults and starting to keep track of which faults are the same fault and which ones are different faults. So I'll use different names and different colors, and I'll illustrate this in a moment. And then generation 3, I'll use the generation 2 faults that I picked on time slices, redisplay them on vertical lines, and fine tune or refine my fault picks. So here is an inline 1800. There's some obvious breaks in the reflection patterns there, and a little bit more of a subtle one over here. So for generation 1, I don't worry about breaking out individual faults. I'll use the same generic fault. So fault F with a green color. So I picked it 3 different fault segments on this line. And then here is a cross line, and here is a fault in this location. It's got some reverse offset on it, normal fault over here. So now I can do that on 5 or 6 lines. I can take the seismic display away and just look at the fault traces that I've manually picked, and there's not much of a pattern there, not yet. So that's generation 1. What I'll do is work on a composite display using the time slices. So here's the reflection amplitude. And so blue are increases in impedance, reds are decreases, and whites would be close to 0. This is the coherency for the same time slice. And again, the darker bands are low cross correlation and candidates to be faults. And what I'll do is I'll co-render. I'll put the reflection amplitude on the computer screen first, and then I'll overpost the coherency. But if it's a high coherency, white or light gray, I'll make those values transparent. If it's dark gray or black, I'll make them opaque. And so that's what this is, a co-rendered amplitude and coherency. And so you can see that the black lineations also look like places where the red, white, and blue reflection amplitude bands are broken. So I'll post my generation 1 faults, and they'll show up on the time slice. And now I can start correlating second generation faults. So that might be my yellow fault, that might be my cyan fault, my orange fault, and my magenta fault. And this is at 1160. I can look at 1164, 1168. Usually I don't look at it that densely. I might look every 20 milliseconds and start looking for patterns that correspond to the yellow fault, the cyan fault, the orange fault, magenta fault. So here is a time slice 1220. The green is my first generation fault picks. I can see where some faults are located. It turns out, I believe this is the yellow fault, this is my aqua fault, this is my orange fault, this is my magenta fault, and now I have a light green fault that I'm picking down here. I can look at what I've done thus far, turn off the seismic. The green fence posts are my generation 1 faults that I haven't worried about separating. The rails of the fence are what I picked on time slices. And so you can see I have a yellow fault here. This is where the cyan fault is located. C is the orange fault. D is the magenta fault. And E is the light green fault. And so I can do this process, work around the entire 3D data volume, and come up with a fairly consistent series of major offset faults in a relatively short period of time. We don't like to rely on faults picked on time slices because when we generate coherency, there is some vertical smearing of the data. So I'll post my second generation faults on a vertical line again. And so I believe this is an inline. And so now I can start to get my final faults, the magenta fault, the orange fault, the cyan fault, using the second generation time slice interpretation to give me my third generation final fault offsets. And now I can turn off most of the seismic. I've left one time slice visible, and you can see the rails of the fence. Those are based on the time slices. My generation 3 faults are the slightly deeper yellow, and you can see where I picked that. You can see where I picked the aqua fault, the orange fault, the magenta fault, and the light green fault. So that gives me a start of mapping out some of the major faults here. The next thing is to generate actual fault planes instead of just fault sticks. And most software has tools that we can use. If we give some manually picked fault sticks, it will use either a simple interpolation process to fill it in, or some of the software have what we call smart interpolators that will draw fault planes given some manual interpretation. And what they use is coherency data in order to do something more sophisticated than a simple linear interpolation. So that gives us our large offset faults. We're ready to shift gears and start interpreting some of the major horizons. And so here is Inline 1500. We can identify our major horizons by looking for terminations of reflectors, looking for on-lap, down-lap, erosional truncation, or top-lap. Those are terms that the seismic stratigraphers like to use. There is not too many reflection terminations up in the shallow zone that I want to work on. So another way we can look for candidates to be major horizons is to look for changes in seismic facies or seismic texture. And so as example, I have a fairly dark red here. And so maybe that's a major boundary between this lower amplitude unit and this higher amplitude unit. And I can actually see what looks like it might be an on-lap termination there. So I've interpreted just about a third of Inline 1500. I don't want to get too far ahead of myself, so let me stop there. I'll look at a cross line. This is where the green horizon was picked on 1500. So I'm in this red, and I can manually pick maybe this much. And then it looks like I have a decision. Should I go up on this red, or does it follow the lower red? I'm not sure at this point, so let me just stop the interpretation on Crossline 2200 there. And what I've done is I've interpreted Inline 1500, and then 2000, 2100, 24, 2500. And so I have one inline and 6 crosslines that I have interpreted. Doesn't take too much time to get those 7 little sticks on there. And then I can use an auto tracker to fill in all the data that I have not looked at yet. I set a confidence level and I click the button, and 16 microseconds later, it has interpreted my green horizon through this much of the seismic data volume. And it doesn't go further because I've set the confidence level at 90%. If I had set it at 95, the patch of green would be smaller. If I set it at 85, the patch of green would have been larger. I can look at this interpreted horizon, the green horizon, but I can color code it based on two-way travel time. I've turned the image a little bit. The hotter colors, the reds and oranges, are shallower. The yellow to green to blue are deeper. And so I can look at this and look at other lines to see how well the auto-tracked horizon has done. Always can't emphasize this too much. If you auto-track, always do quality control. So here's a line that was not manually picked. The auto tracker has extended the green horizon in here. And so this looks pretty good on the left. Then it jumps up and down where I have the cycle split or the 2 reds. And then it's consistently picking the upper red. And so this is an area where I might want to go in and do some cleanup. A lot of the software has some tools to help clean up areas where you have some inconsistencies. I think to be consistent, I would follow that upper red straight through there and not try to go down to the lower red as it seems to have done with the manual interpretation that I started with. So if we have a more complex horizon, what we would do is we would break the horizon into different patches, and those patches are separated by the faults that we picked. And so this might be patch 1 to the below a fault that runs between the purple and red line. So I could auto track this region, then I could auto track this region or patch, and then I could auto track this region or patch. So one of the reasons we do the faults first are to recognize where these boundaries are so that our auto tracker does not miscorrelate across a fault simply because it doesn't realize a fault offset is located there. So this is the this is the manual plus auto picked plus cleaned up base of reservoir for the Barracuda structure. The main structure is where the hot colors are here, and the colors that are sticking up through that are some of the different faults. So an aqua fault here, a light yellow, a magenta, a light green, another aqua. There's a fault here, there's a fault here, there's a fault here. So there's about 12 different fault planes, and the color on the horizon surface is two-way travel time. And I can move the display so this cross line can move closer to me, or I can display an inline and move west to east or east to west and make sure everything is being represented properly. So we can extract some horizon attributes, and the reason that we're going to do that is because in the next step we want to look for some smaller scale fault offsets. So I have my horizon that I've just mapped. Again, the colors are faults that are sticking up through the mapped surface. And the attribute that I've extracted is horizon dip. And horizon dip would have X number of milliseconds per trace. The lighter colors are low dip. The darker colors are high dip. And so one reason why we might get an anomalously high dip is because we step across a fault from high side to low side. We're high side of the yellow fault, and then to the north, we're low side. We're high side to the north of aqua, and then we step down. And so we can use some of these attributes, such as dip, to try to look for some faults that are smaller scale than we would recognize in a first pass fault interpretation. So let's focus in on this part of this display of horizon dip. And what we're after now are some smaller offset faults. And so here is a pink horizon. The dip is very relatively steep right here. So it looks like this pink fault could have been extended a little further. It looks like there's a fault that goes through here, and maybe it connects up with the yellow fault, which we see a segment here, and we also see a segment here. Similarly, there's an aqua fault here. This looks to me like it might be an offset, an en echelon fault, but there's a small offset fault, looks like it cuts through there. And then there's something here that all of a sudden goes almost due north and then is here, part of the yellow fault. This, as I look at lines through there, actually is not a fault, but it's a correlation bust where the horizon has jumped to a deeper horizon. So let's look at Crossline 2553, which is the dotted green line. It goes through a place where the horizon dip is relatively large, a possible place for a small offset fault. And that's right here where the horizon aqua color is tracking in the red. It drops down a little bit and continues on. And so I probably wouldn't have recognized this fault on my initial pass. But if this is an important area in terms of reservoir development, I can find that smaller offset fault. Another example, Inline 1851 cuts through here. Here's where that little offset is. Inline 1851, the aqua horizon comes along, and it was not broken by the auto tracker, but now I see that it looks reasonable to have a little bit of an offset there. And it looks like this is projecting down to the fault that was picked down here, the light yellow fault. And then down here where I have high dip, and then it goes to, oops, I'm sorry, hit the clicker by mistake, goes to the north. That's where I have a correlation bust. So the horizon, the aqua, is in the correct red trough here. And then it jumped down, erroneously to a deeper red. I would go back and clean this up by telling the software that no, this at about 1600 on the far right is where that aqua horizon should be. So I'll have to go in here and surgically edit, remove the incorrect correlations for the deeper red trough and go back to the shallower red trough. So going through this six-step process, I then come up with a faulted framework. I have all of the major and some of the minor offset faults. I have all of the major stratigraphic horizons. And so now I have a faulted framework, and that is the skeleton of which now I'll start to focus in on a potential reservoir unit or a potential source unit or a potential seal unit, and continue my in-depth analyses. So this is a display through this same data set. I have a inline here, 1900, north to south. I have the green horizon, the aqua horizon, the orange horizon, the yellow horizon, and I have a fault, the red fault, and I can look and QC how well the four horizons have been mapped, how well the red fault has been mapped, and I can also QC the intersection of each of these horizons with the fault on the downthrown side and also on the upthrown side. So that brings me to a conclusion of the prepared statements. So I'll turn the microphone back to Dr. Bohan. And here is our syllabus in case we need to refer to either past sessions or what's coming up next week.
Thank you, Fred. That was very interesting. It was very straightforward, I thought. If people could write questions in the question box while you're writing your questions, I have a quick question.
Sure.
Like I said, it seemed very clear and well broken out as to how you move through that. That being said, are there any common mistakes that people often make or things that they need to look out for that you can kind of give us a heads up on?
It does take a lot of iteration to make sure that the fault picks are all consistent and the horizon picks are all consistent. And so, if anything, my lecture here has given you a false sense that, oh, this is pretty easy and I can interpret a 3D volume in maybe a week or two. I've used fairly easy to map a series of faults, and I've used fairly easy to map horizon in order to illustrate the basic steps. But it could take several months to interpret a reasonable size 3D survey that might have 50 major faults and might have 20 significant horizons. And working the data does take time and effort if you want to have a quality product.
All right, thank you. We have a question from Jason, and he says, how do we know when to stop interpreting for fault horizon? And what are the pitfalls we should avoid for that?
Yes, a lot of times you have a deadline and you have to be finished with your interpretation by October 18th. And so usually what interpreters always run into is that they could get more detail and more refinement if they had more time, but they just don't have that, that luxury. And so one of the things I didn't mention in the recon phase is that you want to evaluate the data quality, and you want to consider what sort of products are they expecting out of you, and to make an estimate, you know, is this reasonable? Can I give them 25 faults and 15 horizons in 7 weeks of interpretation time? If you don't think that's possible, then you need to talk to people and alert them early rather than late that, hey, if it's just 3 interpreters you have assigned to this and you want all of this work done in 7 weeks, we're not going to be able to accomplish that given our understanding and our reconnaissance. So either you have to give us a couple more weeks, or instead of 3 interpreters, maybe we need to get a 4th interpreter.
That makes sense. Thank you. So we have a question from Joanne, and she wants to know, how much do you need to keep changing the gain of the display in order to do the interpretation? Are there guidelines for this in order to save time?
There are not guidelines because the gain and the color scale that you use and all sorts of display parameters vary from interpreter to interpreter. So some people like a red to white to blue. Other people like different types of color bars, depending on whether you're working on the, let me go and get a slide here. If you're working on the deeper package, where the word reservoir is, this gain setting might be okay, or you might want to decrease it a little bit. If you are assigned to working the seal and you want to know how continuous the seal is on the top of this structure, the seal has a lower seismic response, lower amplitudes. So you might want to boost the gain if you're looking at the seal. Source rocks intervals tend to be low amplitude, and so again, working the source rock intervals, you may want to change the gain. My experience when I'm interpreting a data set, I usually play around with the gain the first day or two, and then I get something that I can kind of live with, given the objectives of my interpretation. And normally I do not change the gain very much unless there's a particular feature I'm trying to enhance or that I feel is too bright and I need to cut the gain back a little bit.
That makes sense. Thank you. Our next question is from John, and he asks, are all of these maps done using a single software or a combination of several softwares?
The example I went through today is all with one software, and what I've been showing you are displays out of Voxel Geo, which is a paradigm geophysics software package. And so that is one of several interpretation systems I had available to me when I was working on this for ExxonMobil. And it was the software package I preferred. No package has every feature that you would like. Each software feature has its pluses, and each software package has its pluses and its negatives. And so it depends somewhat on the interpreter or the interpretation team. If you are working an area and there's 3 interpreters, you would have to agree on which software package you're going to use, because it can get very messy if one person is using package A and the other 2 are using package W.
All right. Our next question is from Jason. He says he's heard about the method called ant tracking, and could you elaborate on that?
Yes, ant tracking is a system to try to correlate faults through a 3D data set. So I showed an example, where I had some manual interpretation, and I used a horizon tracker to try to expand and save me a lot of interpretation time. Ant tracking is an approach that tries to do the same thing with faults. Faults are not as easy to auto track as horizons. And so there are a number of different methods that different companies use, and ant tracking is one that a number of companies have used. I think I saw my first ant tracking result probably in about 1998, and I wasn't too impressed then. But of course, the software has evolved and improved and become more user-friendly and more accurate. And I know a number of interpreters are very happy with the ant tracking type of approach.
Wow. 1998 was 20 years ago. That doesn't seem possible. All right. Narsaya asks,
you're an old guy.
how to handle the intersection point of fault and horizon in the case of a reverse fault where the calculation of dip is problematic.
Yes, reverse faults have a problem with the software, at least in the earlier days, because you could have a repeated horizon. So let's just say we're mapping the top of the Mississippian. You could have a reverse fault where the top of the Mississippian has a shallower depth or two-way time on the hanging wall side, and it has a deeper depth or time on the footwall side. So the earlier software packages, it was written into the code that one horizon could only have one value at each XY location. They ran into this problem whenever people started working thrust faults, Rocky Mountains as an example. interpreters came up with their own method to try to solve that limitation. The software companies picked up on some of those tricks. And so most of the modern software packages allows you to handle horizons that have repeated time values at a certain XY. So it is a little bit more difficult using mapping in reverse fault terrains and thrust fault terrains than it is in extensional basins.
That's good to know. All right, we don't have any more questions. So I'd like to go ahead and close up and once again thank Fred for his time and for giving us this incredible resource. And I want to remind everyone that the next webinar is going to be September the 5th on stratigraphic hierarchy. So we hope to see you all there. Thank you, Fred. I hope things in Houston continue to improve for you guys.
Thank you. Yeah, we are starting to dry out, and some of the roads are still closed. Some of the rivers have not reached peak flood stage yet. So there's a lot of hurting people, and although the rain has stopped, continued, the flooding is expanding in certain areas. So it'd be nice for people to keep the Houston, well, it's not just Houston, all of the Texas Gulf Coast in your thoughts and prayers. And I'm sure if you would like to, you could donate some money to an organization like the Red Cross and help with some of the disaster relief.
That's a good point. And that's it's a good reason to think about the hazards that we have in other parts of the country and make sure that we're prepared for disasters that we don't want to think about and weren't sure were going to happen. So please stay safe.
And if anyone is going to start to work a career and you're going to move to Houston, get flood insurance.
All right. Well, thank you, Fred. And thank you, everyone, for joining us. We'll see you next week. Take care.
Okay.